So again, welcome all to our events. My name is Rajan Sabrbek. I'm the chair of IEEE ComSoc student badge at ASU. Um, the mission of our branch is to connect high-level experts with the students and professional who is interested in the field of communication, networking, and wireless technologies. And as a part of this mission, we are hosting our keynote speaker series. And today we're excited to welcome our first keynote speaker, Professor Kunes. Um, so before she continues with her presentation, I would like to introduce her for a bit. So Professor Kunes brings deep expertise in satellite networking and space security. She's a Tier 1 Canada Research Chair in New Frontiers in Space Communication and a professor at Polytechnique, Montreal, Quebec, Canada. She is a director of the Polytechnique Research Center and is co-founder and director of education and training of Astralis, the Disciplinary Research Unit of Space Resource and Infrastructure Engineering at Polytechnique Montreal. She is also an adjunct research professor at Carleton University, Canada, and Professor Gunes received a Bachelor of Science degree with high honors in electronics and electrical engineering from Boğaziçi University in Istanbul, Turkey, in 2000. And she also has Master of Science and the PhD degrees in electrical engineering from the University of Ottawa in Canada in 2002 and 2006, respectively. She worked in different technological companies in Canada and Turkey between 2005 and 2010, and from 2010 to 2021, she was a professor at Istanbul Technical University. And now Professor Gunes is a Marie Curie Fellow, and she received a Turkish Academy Award of Outstanding Young Scientist in 2019. So today her presentation is titled Towards Secure and Sustainable Non-Terrestrial Networks to Bridge Earth and Space. And so feel free to ask your questions, unmuting yourself after the presentation, or if you have a question during the presentation, please type it in the Q&A box. And without further ado, I want to hand the stage to Professor Gunes.
Well, thank you, Arisa. This is a fantastic introduction, and thank you for this kind invitation. I am also delighted for this opportunity because I've been also trying to seek an opportunity to work with professors. Let me tell your last name properly, Eleni.
Just Irene, just Irene.
Because it's I think this is a good opportunity to discuss in this environment. I'm looking forward for your questions and discussion points. I will be presenting more problems than the solutions, so it's a lot of there's a lot of research opportunities I see in the field, and I'm hoping that maybe we will find some collaboration opportunity to work with Irene in the future in the technical side, as well as we have been already working in a lot of administrative aspects. So with that, I want to let me start sharing my screen. Wait. Not the Outlook, not the okay, yeah, it should be okay. This should be the presentation. Do you see it in full screen?
Looks correct.
Excellent. So if you guys want to ask questions during the presentation, and if I don't notice it, you just ping me, or I will be happy to answer them, or I can take them at the end. Again, delighted to be here. I will be talking about today mostly what goes on in space. It's more on the discussion about the how we expect this evolution, and if we zoom out to each and every part of these links, you see communication problems will be popping up here and there. So that's the focus that I would like to keep today. And so in the presentation, first of all, if you are currently I'm not based in Canada for about in about 4 months or so. I will go back. So if you want to ever visit us, I'll be happy to host you. So that's why I want to start with our introduction in the presentation. Then I will talk about some abbreviations. This abbreviation is the most frequently used abbreviation is NTN, or maybe from the standards perspective. So I'll try to give a perspective on how and when they are used, and also mention about new space. And I can see this is the ComSoc student branch, so I'm sure that you guys have a lot of brilliant ideas. So I would like to highlight these opportunities about new space. If you want to start your own company, there's a lot of options going on there. And then I will move on to a bit of the I'll say the complaining part, mostly like what is going on in space. But I will talk about 4 different S terms that start with S: security, safety, sustainability, and stability. And these are somehow integrated. There you cannot separate one definition from another definition. That's mostly because space systems are like distributed control systems. So that will be the part where we will look into how to transfer information between these satellites, and then I'll just conclude with a 1-page takeaway about the topics that I will be discussing. So, first of all, I'm where I'm located. I will be located maybe at Polytechnique Montreal. We are an engineering school based in Montreal. If you were in Montreal during ICC, maybe you have seen the mountain. That's maybe a large hill, but we call it a mountain. And our school is located on top of this mountain. We are composed of 7 different departments on the engineering, and one of these departments is my department, the Department of Electrical Engineering. The green floors that you see in the picture are the electrical engineering parts. In total, with 7 departments, we have about 10,000 students, very diverse in terms of the gender, in terms of the nationality. We have about a quarter of our students PhD and master's students. Regarding the size, that about 2,300 diplomas are issued every year, and our school has been operational for a very long time. The teaching aspects, of course, are critical, but we are mostly a research-intensive university with very active researchers and very active hands-on development. So in terms of this hands-on development, on my end, my background is on wireless communications and wireless systems in the end, and I'm part of Polygram Research Center, as I mentioned. Polygram represents Groupe de Recherche Avancée en Micro-ondes Électroniques Spatiales. So that's basically microwave and space electronics research laboratory. It was founded in 1992. It is one of the largest RF research centers globally, mostly from the fabrication side. Currently, we are 12 professors. Since last November, I have been serving as the director of our research center. So in our research center, we can do multiple functionalities, starting from the design of the circuit up until fabrication and testing. We have clean rooms, we have anechoic chambers, we have precision machining, and also the systems that we can test can go up to 1 terahertz in reception, 1.5 terahertz in transmission. And our systems are also reservable from this from our shared infrastructure website. So in terms of the Polygram, since I joined this about 4 years ago, I started also including more system level let's say testing research and testing facilities, and those are mostly in terms of the software-defined radios, and we do wireless system testing. On my end, as in my particular research group, I work on space systems. Most of the applications rely on communication, but some applications are beyond communication, like energy transfer and radar. So my research has been funded by the Canada Research Years. But thank you for the good introduction, and you mentioned all of most of these things, so I can skip them. That one of the more interesting things I find is I started working on a bit of a combination of these multiple functionalities. Like, for example, when we receive the signal, we get the in-phase and quadrature data, and this data has a lot of things. It has energy, it has radar or the information about the channel, and it has communication. So I'm trying to look at its holistic perspective and try to divide topics into different aspects. Each of them, of course, when you combine everything, it becomes like a big blob, so it is not that easy to concentrate, but each of these things can be different and can be focused separately. So one of the things that I would like to mention, that I have been also working with some industrial partners. One of our industrial partners is Volta, which is founded by I'll say new generation of entrepreneurs, and with them we are trying to look at how we can send energy from the orbiter around the moon to the rover on the surface of the moon. So these things that actually look like a bit of a science fiction are becoming reality, and these can be more formed into business plans, and can find investors, and it is very exciting things are happening. So this is the reason that I wanted to highlight this topic among this student branch talk, because the new problems which will be introduced by new space are very exciting, and much more reachable than it was in earlier times. So other works that I do is on satellite resource allocations with MDA space, and network design with TARSTAR solutions, which plan their own low Earth orbit constellations. But overall, this is the research philosophy that I'm trying to do is, when we have an object up in space, is it possible that we can use the same object from multiple different perspectives? So similar to a Swiss Army knife, how like that has a lot of different features, that has a little knife, that has a little can opener and things like that. So we can maybe try to use this same philosophy in space design. So going back to the extension of the topic, this is the term that we keep seeing from apologies. This is the term that we keep seeing, new space. What is new space? So formally, space missions have been planned by the space agencies. So these are mostly national space agencies, and within Europe there is international cluster which is called European Space Agency, that is collecting multiple countries. So they have been they are the ones that have been responsible from the space mission planning, and there were few private companies. But in the last 5 years, as you can also see from the news, there have been a lot of action happening because of the emergence of private companies that they want to do their own space systems. So these companies, they focus on their solutions being low cost, their cutting edge innovation, and of course, it needs to have a sensible business plan. So it needs to be commercially driven. With that, they bring a new perspective to space exploration, space services, and also they provide new technology. So there are different ways of classifying these new space companies. We can classify them according to the orbits. We can classify them according to the services that they provide. And also based on their sizes, of course. So what I have been seeing is most of the if you go with a classification of according to the orbit, there are suborbital companies that they do space tourism. There's orbital companies that actually try to do more of a constellation and mega constellation designs, like low Earth orbit satellite based designs. And then there's the deep space companies that are a bit less conventional, but they are coming along. So what they want to do is they want to use their designs in a competitive way in the market, and they want to have reusability so that they can reuse the same design over and over again, to mostly because of the cost perspective, and they would also like to have this scalable. So with this, there's a new generation of space companies that are coming into the picture. These are transforming the satellite industry. Satellite industry is basically what has been synonymous with space industry, but now, as you can see, there has been a more of a divergence between them. Now, this new space is being pushing in terms of the communication perspective, these new constellations on using satellites. A satellite is a human-made object launched and orbiting around the Earth. Of course, it can orbit around the Moon and the Mars, also other planetary bodies. But this is, of course, we are talking about artificial satellites as human-made satellites. Most of the satellites that we see these days, we talk about these days, correspond to low Earth orbit satellites. They are the satellites with altitudes of about 450 kilometers up until 1500 kilometers. And this is called the so-called the LEO belt, low Earth orbit satellite belt. First, these satellites are, especially with I know that we are recording this, but it's not like a publicity or anything. But most common one that you can see every day and you can see at the night sky is SpaceX and Starlink constellation. So these constellations are composed of thousands of satellites, and because of the scalability of the launch, these say cycle, they are we can see more and more satellites up in the space. The main innovation that has been pushing this is the improvement in the payload architecture, the improvement in the antenna systems. We have better active antenna systems. That's basically like a beam forming, updating the coefficients if you are working on resource allocations, like beamforming rates, and updating the frequency of these beamformers. We can do better digital and optical processing. We can do better energy management through solar panels and batteries. And finally, we have a better connectivity through the ground segment. So there's the space segment and the ground segment. Ground segment is basically taking everything to the core network. This is basically what's happening. And on the right side of this slide, you can see that I'm showing a map of Canada, a bit of the US, and this is the points are representing a snapshot of the Starlink constellation. As you can see, there is a significant coverage up in this like very highly populated belt in Canada, but up north you can see that there's still a significant coverage gap. So with this, we are trying to actually cover everywhere, and we need to do a bit better to be able to cover the polar regions. So what is the main difference? The main difference is now the one satellite can work with another satellite and they can actually do networking. These days, the networking that we do is not as sophisticated as the terrestrial networking, but through the use of optical inter-satellite links, one satellite can send high data rate information to another satellite using these optical satellite channels. So now we have reduced costs. We have better, let's say, capabilities on per object, say, perspective. What are we doing as humanity? We keep sending more and more satellites up to space. So this is the data that I get from NASA that is keeping track of the space objects. They have their catalogs, and this graph clearly shows the exponential trend, especially in the LEO band. The other bands are medium Earth orbit, and there is also a geostationary Earth orbit that are farther away from the Earth, about 36,000 kilometers. So this graph is actually showing that in the with the let's say increasing popularity of new space, we can see that all these new startups and also the investments and also the business models are pushing humanity to send more and more objects up in the space. So this is the reality. That's not the research part so far. What can we expect from the research complements to these systems? First of all, we will be expecting new networking elements. Why do we need new network elements? Because if I go show this constellation again, we can actually we are very good at satellite to ground, ground to satellite connectivity. Satellite to satellite connectivity is also very efficient, but running sophisticated routing algorithms, instantaneous decision making in satellites in a collective manner, those are the things that we need to still improve. So with that, we may need additional components that can help us operate these networks better. The first component, and also has a lot of other additional capabilities as expected, is these low altitude platforms with an altitude of say up to 400 meters, and they are basically these uncrewed aerial vehicles, uncrewed aerial systems, or so-called drones. They can actually help these networks, or they can be user equipment by themselves. Another component is the middle one. There's this stratospheric platform, so looking at altitudes of 17 kilometers up until 50 kilometers. And these stratospheric platforms, currently they are not very much used, and I'm a big fan of this, so I would like to explain why I think they will be useful. So when we have this very dense terrestrial network and a very dense aerial network, I am imagining this like as two layers of cookies. So to be able to glue them like an Oreo, I think we need another layer so that we can actually send all this management information up to space in an effective way, and then from space back down to Earth. This is critical because of the mobility management, security solutions, and all the other control information is very difficult to manage up in this satellites. So for why is that? Because each satellite, a low Earth orbit satellite, can illuminate one specific cell for about 7 minutes maximum. So after 7 minutes, that needs to be swapped with another satellite, and that's the reason that we need so many low Earth orbit satellites to have global coverage. So that is the current paradigm. what is happening also on top of this is on the right side, you can see that there is also another new trend is happening in the satellite domain. These are the very low Earth orbit satellites. So very low Earth orbit satellites will need to be between the orbits of 150 kilometer up until the LEO belt, which is like 400 kilometer altitude. So a LEO satellite travels around with a speed of, let's say, 26,000 kilometers per hour, which corresponds to 7.6 kilometers per second. And a video satellite travels with about 32,000 kilometers per hour. So they are much faster and they are very close to us. They need to be faster because to be able to stay in the orbit so that they don't fall to our head, they need to move very fast. So this is another, say, trend that we can expect in these satellite systems. So this is actually somehow coming true because you can also read about the Starlink's plans of reducing their altitude from they say 550 kilometers up until 400, down to 400-ish. Because if we keep the satellites closer and closer to the Earth, the distance that the signals will propagate will be shorter. So actually, the signals can be received with higher strengths, and that can lead to higher data rates and reduced latency. So that is what we want to do. We want to use actually our regular cell phones to connect to the space. And for this, there are so many different standards that are being studied by different organizations. So the most popular one, as I understand, which is the most promising one, is when you are out in the woods, you get your cell phone and you want to actually connect to the satellite. This is called this is usually referred to with the abbreviation of direct to cell or direct to satellite, and you can actually use your own cell phone for that. Most cell phones actually do this with messaging, but now we are trying to reach like 2 megabit per second data rates. So this is the standard that has been pushed by the Third Generation Partnership Project. And when you hear this abbreviation NTN, representing non-terrestrial networks, that is the extension of the cellular system evolution. So this direct-to-cell, direct-to-device is targeting this kind of standardization. Now, mostly starting with low data rates. However, of course, there is a competition. If you go out to a cabin, you can use a better device than this one. So assume that you get a big satellite, a big antenna array to be able to connect to the satellite, and that will give you, of course, higher antenna gain. And that standard is the other, let's say, alternative that has been pushed by European Telecommunication Standard Institute, and that is the evolution of digital video broadcasting standard. So DVB-SX is higher data rates, but you need to have a specialized terminal. So you cannot actually use your phone, but you need to have a specific antenna array, and then you can connect to the satellite. So this is basically what we have in terms of the standard. So I also, if I go to a store and get a Starlink terminal, or if I want to use, let's say, Amazon, subscribe to Amazon Leo, what will happen? That is another story, because there are also additionally proprietary solutions, which basically implies that their air interface is not standardized, and there are you can see a significant amount of papers that are representing their findings about the reverse engineering of these proprietary solutions. So they exist in the literature. So this is very fragmented, as you can see. It can be complementary, so they need to somehow work together. But the main problem that I see in these setups is even when I'm mentioning standardization, assume that we have this I'm going out to the woods. I want to use my cell phone. What would happen? So I will be able to connect to my from my cell phone to the satellite. Of course, the satellite should balance the link budget. There are different techniques for that. One of them is using a very large antenna array on the satellite side that is being uh, tested successfully by AST Space Mobile. That's excellent. So what happens next? Now, when my signal reach the satellite, and the satellite will take this signal back to Earth, most likely, or maybe to the next satellite and then back to Earth. So this part is called the feeder link. From the satellite back to the ground station, and from the ground station we may have like fiber optic terminal cables that are taking the data back to the central network. The problem is, even 3GPP has been defining the front end. The satellite to ground station part, the feeder link, does not have any standardization. And also the satellite is moving very fast and also sending this data over a wireless communication channel. So that means the connectivity can be intermittent, that can be fading. There's no proper standardization at this point. Hopefully it will not be true anymore, but as of now. And then, of course, when we are talking about VLEOs, then it will need to, which is basically the trend that is coming, or lower altitude satellites, we need to switch between all these satellites very fast. So this is an obvious gap. And in terms of the standardization part, Open Radio Access Network Alliance, Open Radio ORAN Alliance, they are trying to actually come up with additional recommendations and standards to be able to address these problems. So ORAN is also another abbreviation that you have already heard perhaps, but if not, you will be hearing very a lot. They are suggesting, this alliance is suggesting a disaggregated, so distributed, open, all the standards are available, and intelligent. Intelligent meaning there are the sufficient hooks to include artificial intelligence machine learning algorithms. So they provide this architecture for mobile networks. And this is complementary to 3GPP's radio access network. And additionally, explicitly defines all the interfaces. And they have these these RICs, which are called Radio Access Network Intelligent Controllers. And using these RICs, machine learning algorithms can be deployed in these networks. So the problem between such a network and the existing highly functional, let's say, well-functioning terrestrial networks is that these feeder links are open, so they are actually communicating, sending all these signals over the air. So when I was talking to a network operator, terrestrial network operator, they were telling me that once the signal reaches the base station takes a signal to their core network through their own fiber optic cables. So in those cases, even the signals they don't need to encrypt the signals. But now, of course, we are sending it over the open area, and also there's a highly likelihood that we can actually lost packets in this transmission. So we need to actually do a new network design. This network design requirement on the control side, or on the feeder and backhaul side, is mostly introduced because of the mobility that is inherent with these satellites, and also the scalability. That means as we keep increasing the number of users, we will need to accommodate more and more signals, and we need to somehow find a way of addressing all of these. For instance, if a satellite would like to provide access to 2,000 users, the satellite will serve only for 3 minutes. So if we only use, like, even if we use let's say 20 milliseconds for each user, most of the time we will need to use for access control. And of course, there is the round trip time. So it is not the current architecture as we have it is not scalable. Another problem that I need to mention is the space technology, the processors, space grade technology. Let me put it this way: space approved radiation hardened processors. They are about 10 years behind the current technology. So think of your computer 10 years ago. That's basically the amount of computation that you can do approximately with a satellite. Or if you want to have a parallel running processors, then you need to coordinate that, of course, very carefully. In addition, to be able to send control data, you need to send over the air, and that also introduces a lot of delay. So we cannot actually, let's say, control everything. So at the end of the day, if we these are all the problems. But what is happening? So in space, as I I will. This is the part that I will start to complain about the solutions that we need to find. So this is basically the objects that are cataloged in space according to their orbits, and you can see that there's still a significant amount of objects at this point, and keep the fact in this that we cannot track objects less than 10 centimeters because they are too small, so we don't have a reliable catalog for these small objects. So yeah, so this is basically what we have in terms of the deployment. So what I would like to see for going forward, I mentioned about this multiple functionality. So this is a picture where I would like to explain that. So when we send a satellite to space, usually the current satellites, they have satellite to, of course, ground to satellite connectivity to the user, to the gateway, and then satellite to satellite connectivity. But since these can serve for all these users, maybe we can also add additional features so that the satellite can perhaps bounce the signal towards the moon, maybe towards the other destinations, so that we can make use of this satellite for multiple purposes. So one of the main problems for lunar exploration is the fact that we lose communication, especially when the missions are planning to land on the South Pole. So if we can use the satellites that are already around the Earth to extend our coverage, it can be rather useful for us. So this is basically the mindset that we can try to extract the most benefit when we send these objects to space. So how does it affect in terms of this 4S perspective: security, safety, sustainability, stability? What I can tell you is all these definitions are so much intertwined. So you cannot separate one definition from another definition. And one of the best documents that we saw with my PhD student Nesrin is this noted reference. So as you can see, sustainability has a definition, safety has a definition, security has a definition, and there you can see the overlap between them, and also the stability. From the stability part, I would like to highlight the fact that actually satellites are remote controlled robots. So you can actually change the orbit, change the altitude by igniting the propulsion engine, and you can control its position up in space. So that introduces an indirect control problem to the discussion. So the stability becomes an issue even with that. So when we look at the vulnerabilities of these systems, except from the fact that we keep sending thousands of them, vulnerability points can be on the satellite, vulnerability point can be on the inter-satellite link, on the ground network, and finally on the end user. And if you read a security survey on satellites, this is basically the classification, roughly the classification that you can see. Now, here I would like to go back to the Open Radio Access Network Alliance deployment suggestion document, which was published in, I think, on last April. So they talk about how O-RAN can be deployed in non-terrestrial networks as the evolution of like as NTN deployment strategy. And they mention, of course, when we deploy this, there can be security challenges because of data integrity, unauthorized access, eavesdropping, jamming, kinetic threats always in satellites, denial of service, distributed denial of service, spoofing, handover, network risk, supply chain security, and the list goes on and on. So they actually say this is not a comprehensive list. So the main the part that I blame for this incomplete list is the wireless channel, because over this wireless channel we send this information. It is prone to leakage, and it is prone to active attacks that can be actually misinterpreted by either the satellite or the ground station. So here I would like to give an example of what can happen. Most of these attacks or what we observe in space are thanks to amateur radio astronomers. So these people, they have their own telescopes. They look at night sky and they observe what goes on in space and they report it. And of course, thanks to them, we see a lot of things that are not officially disclosed by nations due to different concerns. So this is this event that I would like to talk about is happening in the GeoBelt. GeoBelt is the geosynchronous Earth orbit. So this is the orbit where satellites are moving at the same speed with respect to the Earth. So we see the satellites stationary, and geosatellites are almost assumed to be stationary. But as we can see in this picture, the TJS-3 has been spotted to move between two geosynchronous satellites. So that means even in the GeoBelt, satellites can move. So we need to actually understand that, or maybe take into account that they can actually go beyond their orbits, and the rest of the systems should be designed that way. So this can create different kinds of problems. One problem that it can create is the eavesdropping. So if a signal is sent from the user to the satellite, that if there is a space plane that can capture some of this signal. And of course, with this capturing the eavesdropping, it's usually said, okay, if we use free space optical communications, it is very secure. That is not necessarily true, because through mirrors and through, objects that are capturing some of the signal from the signal transmission path, some of this signal can be leaked. So, new kind of security systems that needs to be taken into account. Another problem that I would like to highlight is, okay, eavesdropping is an issue. Another issue is what happens if these devices start signals that are blocking communications, like jammers, or even worse than that, trying to do some smarter attacks. So, for example, if a high stratospheric platform that is close to Earth somehow gets attacked and it turns rogue and starts sending jamming signals, then we can easily lose coverage of tens of kilometers of regions. So these are the things that we may need to consider when we are looking at the design of these systems. And same kind of attack scenarios, they don't have to be on the Earth side. These things can also happen in space. So there can be active attacks in space, which haven't been reported yet, but I don't. They can happen. So in this setup, the signal, or maybe based on the spatial characteristics and orbital dynamics, we can actually try to understand if the received signal is actually what we expect it to be, or it is something different. So this can actually be used to understand or alert the system.
Ines, we
10
have
minutes.
15 more minutes, so I want us to make sure we have time for questions. So
Yes, yes.
Thank you.
In 5 minutes, I'll do that. Yeah.
Great.
Thank you. So, this is the good things are obvious. So what is happening on the bad, the critical side? So, for instance, if a high altitude platform station captures all this signal in this particular link, to block this whole area, and jammer can just block this backhaul, and the whole cell is blocked. So you can see that there needs to be a different mindset in this kind of systems that needs to be considered. So basically what I'm trying to say is we need to think of these safety, security, and stability in different way. You cannot say, okay, it will follow this order. We can do a different design. So one of these designs is the secure by component. And it is highly important that we don't do patch solutions that we use in terrestrial networks. So by the time that we launch an object, we need to make sure that the design is fully secure. So there are some work that is nearly starting, and there is a new standard that is coming up if you are interested in this security perspective. Now, once the security is done, let's say assume it's done, what is happening? So I was mentioning these satellites are robots in space. So how do we control them? We don't have a distributed control plane. We control each satellite by the ground station. So overall, we need to understand what goes on in space. So that relates to this not new, but newly commercial paradigm. Mostly it has been in the military sense, which is called the space domain awareness. So basically, we need to understand what is happening in space. One of the examples that I have is this. There is a small hole spotted on Canadarm, and nobody knows where this came from. So there's an object that is moving up in space that's just emerging based on this damage. So we can see that there's a lot of objects, there's potential collisions, a lot of interference, debris is there. When we try to connect from the ground, we have limited capabilities, and there may be even potential attacks. So how do we actually manage this network? So this is the part that I would like to take my 3 more minutes before going to the final part. So we need to have a new kind of, of course, this is almost like an IoT network, but a highly mobile IoT network. But how should we understand what goes on in this sensing network up in space? We can have data sources, we can have actuator nodes, we can have network nodes, and we need to manage this sensing and communication through this network. So how can we do that? One way that has been usually done is take all the data back to the ground. And the second way that is mostly discussed in papers, keep everything up in space. And of course, potentially, there is a mix and match of these two that is doing a hybrid network. So we try to understand as a observation proxy, we looked at the distances and try to understand how much time on the average that we can take to take this data back to Earth. Regardless, I'll say almost regardless of the constellation size, we take about 60 milliseconds to take this data back to Earth. But if we want to collect this data up in space, then the constellation size changes the performance significantly, and we can reduce this data communication time from 60 milliseconds to 1.32 milliseconds. So this is the on-orbit architecture. So overall, basically, we may need to do this distributed setup, but of course that requires more coordination. And that also, on top of it, we may need to add more hierarchical decision making. We need to make sure that they are reliable data. So there are so many additional problems on top of it. So in the long run, the question that remains is, how do we future-proof this? Of course, new space is fantastic, but how do we design a sustainable network? We can introduce different functionalities to all these nodes, but of course, this is not like a one-paper job. This needs to be accepted in a universal manner, or maybe at least in the Earthwise manner. So this has made us think about this new requirement of this new standard because of all this fragmentation. So in short, with NESIN, we are starting this new this standard on collaborative orbital data sharing. So how, at least try to give some ideas about this data sharing between these operators. And if you would like to have more information about that, I would be happy to provide. There are so many problems, and of course, even starting a standard is not that easy, I'll say. And from the geopolitical tensions, as you can see, there is only 4 countries have so far accepted not to be the first to put weapons in space. So what is happening is my main message: standardization is the key. Let it be standardization on communication, let it be standardization on security, and also data sharing. And obviously, we need to enhance international collaboration, and spacefaring nations need to share their best practices. This I see as the only way that we can keep space sustainable. There is one paper that paper call that I would like to mention. That's on June 1st. That's the submission deadline on TESS on secure, resilient, and sustainable space networks. So, and with that, I would like to thank you for your attention, and I would be happy to take your questions.
Thank you, Professor Gunas. That was an incredible presentation. That was a lot of useful information. And